Okay, what are those things? Uh, hey, similar triangles. And we're going to use geometric means. So the similar triangles are just kind of lead up so we can figure out what on earth is a geometric mean. All right, when you hear the word mean, you know it's average. But when you're finding the mean, you're used to finding an arithmetic mean, right? The average you find is arithmetic mean, an arithmetic average. This will be a geometric average. Okay, but first let's look at similarity between right triangles. And if I take this right triangle and I construct an altitude, of course altitudes have to be perpendicular, I now actually have three right triangles in this picture. I've got a small one, and then I'll call the medium-sized one, and then I've got the large one. Right, so the smallest right triangle is triangle BCD. The medium-sized triangle is ACD, and then of course the largest triangle is ABC. And sometimes it helps to cut them up like this, and you say, oh, I've got that small one that I've got in blue, and then I've got that medium one in red, and then I've got my original one that's in black. And all of these are similar to each other. And of course, if the triangles are similar, we know that the sides have the same ratio with one another. All right, so let's find the value of x. Well, if I look at that small triangle, I know the small triangle has a hypotenuse of 3 and a long leg of x. If I look at the medium triangle, well, the hypotenuse is 4, the short leg is x. I cannot set up a proportion with that because I know the hypotenuse. I can compare hypotenuse to hypotenuse, but that's the only thing that pairs up. So let's look at the large triangle. All right, so with the large triangle, well, the hypotenuse is 5, the long leg is 4, the short leg is 3. Aha! I can use the large triangle with the small triangle because not only do I have the hypotenuse, I've got the long leg. So I can compare the small triangle's hypotenuse to the large triangle's hypotenuse. That ratio must be the same as the small triangle's long leg compared to the large triangle's long leg. Right? Those ratios would make a proportion. So plug in the values that I have, cross multiply, and divide, and I get 2.4. Now, normally I would leave it as a fraction, but with this lesson, I've just been converting to decimals. Hey, I could have used the medium triangle and the large triangle because of the short leg. I could have done this differently. I could have said, hey, the medium triangle hypotenuse compares to the large triangle's hypotenuse. The same way, the medium triangle's short leg compares to the large triangle's short leg. Plug in the values I know, cross multiply, Shockerville, exact same answer. All right, same answer. Ooh, a different example. Okay, well, on the small triangle, I have a hypotenuse of 5 and the long leg is x. On the medium triangle, I've got a hypotenuse of 12, a short leg of x. No, I've only got the hypotenuse. That's not going to do it. Large triangle. Hey, once again, I know all three sides. So if I want, I can use the small triangle and the large triangle. Again, set up the proportion. Notice I'll compare the hypotenuse to the hypotenuse and the long leg to the long leg. Cross multiply, divide, and it comes out as a weird decimal. Notice though, I could have used the medium triangle and the large triangle because I know the short leg in each of those, as well as the hypotenuse. So if I wanted to use the medium and the large triangles, the ratio of the hypotenuse and the ratio of the short legs, they have to be the same. Even though that proportion looks a little bit different, when I cross multiply and divide, amazingly, I get the exact same answer again. Find the value of y. Okay, small triangle, I know a long leg and I know a short leg. Medium triangle, I know a long leg and a short leg. So hey, we're in business. Side note, large triangle, the only thing I know is the hypotenuse. I don't know either leg. So don't even think about using large triangle, right? It's not going to work. Long leg, short leg, we're in business. So I'll put the small triangle long leg over the medium triangle long leg, and then I'll put the small triangle short leg over the medium triangle short leg. Hey, look what happens when we cross multiply. We get y squared. Bum, bum, bum. You're getting introduced to the geometric mean. So y is the square root of 40. And I'll come out with an exact answer here. 2 times the square root of 10. So what is the geometric mean? Right, also known as, if you want to think of it, it's a type of average. Right, we've got the arithmetic mean, which is one type of average. The geometric mean is another type of average. And so what we just saw here, of course, in the example, I was using the letter y, but here we got the x. Notice that when we cross multiply, we end up with x squared. So an arithmetic mean would be if we added 2 numbers together, and then after we added the 2 numbers, we divided by 2. Geometric mean, instead of adding 2 numbers, we multiply the 2 numbers. But then after multiplying, we take the square root. Right? So it's still a 2-step process, but instead of adding and then dividing, we multiply and then take the square root. So we're going to try to find the geometric mean of each pair of numbers, and we want exact values here. What if I give you 3 and 12? Well, 3 times 12 is 36. Square root of 36 is 6. So 6 is the geometric mean of 3 and 12. What if instead I give you 6 and 15? Well, 6 times 15 is 90. Square root of 90? Well, let's try 9 times 10. Square root of 9 is 3. Square root of 10, we're stuck with that. So there's the answer. How about 12 and 15? 12 times 15 is 180. The largest perfect square that's a factor of 180. Now, some of you might be able to just kind of do this in your head, but I want to show the factor tree method just for a change of pace. Right, there's different ways of trying to figure this out, but I like to sometimes use the factor tree. And if I complete my factor tree, I can then say, aha, I've got a pair of 2s, got a pair of 3s, I got a leftover 5. Right? Now 2 times 2 times 3 times 3 is 36. That's what paired up. So 36 times 5 is what I'm going to use. Right? Because square root of 36 is plain old 6. Some students like to just list all possibilities, 1 times 180, 2 times 90, 3 times 60, 4 times 45, 5 times 36, 6 times 30, 7 won't work, 8 won't work, 9 times 20, 10 times 18, 11 won't work, and then 12 times 15, right? I mean, you can list all the pairs, but that sometimes it's cumbersome. Or the other method would be, hey, let's go try some squares. Well, 100, no, that's way too big. 81, that won't divide in there. 64, that won't divide in there. 49, that won't divide in there. 36, okay, it worked, right? But that's a lot more guess and check. The factor tree, you're not really doing guess and check. You just make the factor tree and then you'll see what works. So it looks like we're going to encounter a worksheet and IXL. We got an assortment of visitors here. And that should give you some stuff to work with.